Okay, so the next set of topics that we're going to talk about are different reactions that are really critical in organic chemistry. These are called SN1, SN2, E1, and E2 reactions, and we're going to take them one at a time. So first of all, we're going to have to make some definitions here. We're going to have to define some terms, but the first reaction we're going to talk about is what is called an SN2 reaction. And that's a nucleophilic substitution reaction. So first of all, let's define some terms here. And the first term is, what is a nucleophile? So a nucleophile is an electron-rich species. And what I mean by that is that the nucleophile either has a negative charge or it has lone pairs. And remember, the negative charge comes from having lone pairs. So let's take a look at a couple of examples. So for instance, if you have a chloride ion, it has 8 valence electrons. It is electron rich. And what it can do is take this pair of electrons and use it to form a bond. Hydroxide is another example of a negatively charged nucleophile. Its negative charge comes from the fact that it has a lone pair of electrons. So these are both negatively charged nucleophiles, which I'm going to consider to be strong, and I'll talk more about this in a few minutes. But you could even have water being a nucleophile, and in this case it's neutral, but the oxygen is electron rich from its lone pairs of electrons. And so those lone pairs of electrons can be used to, again, form a bond. Now, we're going to react the nucleophile with a carbon that has a halogen attached to it right at the beginning. And the reason for that is simply the delta minus of the halogen, and that leaves the carbon delta positive. So delta plus, delta minus. And what will happen is that this species right here that has a slightly positive charge is what is going to be called an electrophile. And electrophiles are electron poor species. In this case, this carbon is electron poor because its electron density is being taken by the halogen. So that leaves it with a delta positive charge. Now, nucleophile means literally positive loving, and electrophile means negative loving. So that's how we're getting to the idea that an electron-rich species reacts with the electron-poor, and the electron-poor species can only react with the electron-rich. The electron-rich always give to the electron-poor in chemistry. And you can compare and contrast that to real life, but we're going to deal just in the chemistry world. So what will happen then is that the nucleophile is going to form a nucleophile carbon bond, and we're going to break the carbon halogen bond. And the way that we're going to show the movement of electrons is using arrows. And so the arrow that we use shows basically the movement of the electrons. And the electrons move from the end to the arrow. And a full head arrow means that we're moving a pair of electrons, 2 electrons. So in this reaction, what I would do is take this pair of electrons and say, I'm going to give that to the carbon. I'm going to use it to form the nucleophile carbon bond, and I'm going to break this carbon halogen bond and give that pair of electrons to that halogen, which is then going to become a halide ion. Okay, so that is how we're going to write the mechanisms, and we'll do a lot with these arrows. So this is called nucleophilic substitution. I am substituting a nucleophile with a negative charge for a halogen, which is also a nucleophile with another negative charge. So Nucleophilic substitution means I'm substituting one nucleophile for another. So this just shows again that arrow, the idea that the nucleophile is going to take its pair of electrons to form the nucleophile carbon bond, and then the carbon halogen bond is going to break with the pair of electrons going towards the halogen. And so I'm going to form a nucleophile carbon bond and lose a carbon halogen bond. Okay. And so again, in this mechanism, we should have the arrow moving towards the carbon and then the halogen, carbon-halogen bond breaking. Now, the halogen as it leaves is what's called the leaving group because it's leaving. So later we'll expand our view of leaving groups, but for the moment it's going to be a halogen. Okay, so how does this mechanism occur? And in an SN2 reaction, it occurs by what is called backside attack or backside displacement. So this nucleophile is going to come in and it's going to attack this carbon and it's going to kick off the halogen. Now the nucleophile has to attack from behind the carbon-halogen bond. And so that's why it's called backside displacement. And we know that's the case because of our experiments and because of the stereochemistry, which we'll get into in a few minutes. Okay, so that is the backside displacement. Now, this reaction is a one-step, what is called concerted mechanism. A concerted mechanism is when you have the bond formation and the bond breaking all occur in one step. And so it's called one concerted step. And when we have a reaction, basically if we plotted the energy of the products and reactants, and we start with the reactants, what will happen is as the nucleophile gets closer and closer to this carbon, the energy of the system will go up, it will reach a maximum, and then it will go down to form the product. And so in this case, this energy we plot energy versus reaction progress. The tip, the top, the peak of this curve is what is called the transition state. You may remember that from general chemistry. The transition state is the high energy species, but transition states cannot be placed in a bottle and studied. They exist for a quick, fleeting moment, and then they're gone because they are the highest energy species. And the transition state is also where we get either the bond breaking or the bond making or bond forming. Sometimes we'll just have the bond break, sometimes we'll make a bond, but the transition state is where that process occurs. And so in this case, the way we represent the transition state is to think about what is in between the nucleophile reacting with the carbon-halogen bond and forming the nucleophile carbon bond and the halogen. And what's in between that is that I'm forming the nucleophile carbon bond, and I am breaking the carbon halogen bond. And so in this case, what I'm going to get is in between the reactants and products, I'm going to have a point where I have a partial bond being formed and a partial bond being broken. And if you remember back in the resonance hybrids, what we used the dotted line was to represent a partial bond. And so in this case, I'm showing the nucleophile forming a partial bond to the carbon by using a dotted line or dashed line, and I'm also showing the carbon-halogen bond partially breaking using a dotted line. So when we write the transition state, what we're going to do is we're going to average the bonds. and partial bonds are going to get a dotted line or a dashed line, as is shown here. We're also going to average the charges. Again, just like we did for the resonance, for a resonance hybrid. So we're going to have the average charges. So in this case, we're going from a -1 charge to 0, and we're going to indicate that that is going to be delta minus, right? Some charge. Do we know exactly what it is? No. Do we care? No. We just need to know that it is some negative charge, and what's happening to the halogen, it's going from 0 to -1, so it has a negative charge. So in this transition state, what's happening is that we're having a partial nucleophile carbon bond and a partial carbon halogen bond, with the negative charge basically being transferred from the nucleophile to the halogen. Okay? And so that is the transition state for this reaction, and we'll talk a little bit more about what happens with this tetrahedral carbon becoming tetrahedral on this side. What does this middle, what does the transition state in the middle look like? Okay, and what it looks like is it looks trigonal bipyramidal. Now the key is it looks trigonal bipyramidal, because there are not 5 bonds here. 5 bonds to carbon is a huge mistake, because carbon cannot form an expanded octet. So what we have are 3 full bonds and then partial bonds that add up to the 4th one. So what happens is that as the nucleophile approaches this carbon, these bonds will swing out and become trigonal planar. And then as the halogen leaves, and the nucleophile comes in, then those bonds basically end up over here, pointing towards the halogen. So in this case, this is what the transition state looks like. We've got the 3 atoms that were originally attached to the carbon. They are in a trigonal planar geometry, and then the nucleophile and the halogen are basically in a linear geometry. So that is the trigonal bipyramidal geometry for an SN2 reaction. So this just shows you that transition state, the trigonal bipyramidal geometry as we go from reactants to products. Now this energy from general chemistry, the energy in going to the transition state, that is called the activation energy. And that activation energy then, the bigger the activation energy, the slower the reaction, and we'll review that in a few minutes as well. Okay, so now if we take a look at the overall reaction, let's talk a little bit about the kinetics, and then we'll go back to the stereochemistry of that mechanism. So this is going to be a review of general chemistry, probably general chemistry from a long time ago. But let's talk a little bit about this, what is called, how do you determine the overall rate equation of a reaction? And remember, the overall rate equation is going to say that the rate of the reaction is equal to some rate constant times the concentration of the reactants raised to some power. And how do we determine what power that is, or better yet, the exact term is what order the reaction is in each one of those 2 reactants. So what we do is we measure the rate of the reaction, and then we change the concentrations of the reactants and see what the dependence is on the rate. So example, let's say we do experiment 1, and we use 1 molar nucleophile and 1 molar alkyl halide. And let's say that we measure a rate, an overall rate of 1, whatever the units are. So then what I would do in experiment 2 is I would say, well, let's make the nucleophile's concentration 2 molar, keep the alkyl halide's concentration at 1 molar, and what happens to the rate? And in this case, what would happen is the rate would double. So when I double the concentration of the nucleophile, I doubled the rate. So then I would go back and say, okay, let's use, for experiment 3, let's use 1 molar nucleophile, and now let's use 2 molar alkyl halide. And I would measure the rate of that reaction by either looking at the formation of the product or the disappearance of the reactant. And what would happen is I would get a rate of 2. So the rate doubled compared to the first experiment. And then I might be overly ambitious and say, well, let's do 2 molar and let's do 2 molar. And in that case, the rate that I would measure would be 4 times the original concentrate, or 4 times the original rate. So these subscripts or superscripts are going to be the rate order. So when I doubled the concentration of the nucleophile, what happened to the rate? The rate doubled. When I doubled the concentration of the alkyl halide, what happened? The rate doubled. And when I doubled both of them, what happened? The rate went up by a factor of 4. And so the rate equation for this reaction is going to be the rate equals the rate constant times the concentration of the nucleophile to the first power and the alkyl halide to the first power. And so overall, we would say that the reaction is first order in both nucleophile and alkyl halide, but then overall, the reaction is second order because the overall rate equation, or the overall order then, is the sum of the two rate orders for the individual nucleophile, or for the individual reactants. So in this case, this is an overall second order reaction. And the question is, what does that mean? Well, we could also call this second order reaction a bimolecular reaction. And so a bimolecular reaction is one where in the mechanism, which the mechanism is going to be step by step how this reaction occurs, we have two molecules reacting in that key part of the mechanism. And so in this case, this is a bimolecular reaction. Where that comes into play in an SN2 reaction is the following. This is nucleophilic substitution that is bimolecular. That's what the 2 stands for. Now, what does that mean? Well, let me just take a step back. The reason that we know that an SN2 reaction is bimolecular is because the first place we start is measuring the overall rate equation. Now, this rate equation can only be determined experimentally, okay? So if you're going to determine the overall rate equation, you must do that experimentally. It does not come from the stoichiometric coefficients. It is done experimentally. So we do an experiment like what I did up here, a series of 4 experiments. And so therefore that tells me what the overall rate equation is. So that means whatever my mechanism is, there must be 2 molecules involved in the slowest step of that mechanism. And you might say, well, wait, didn't you tell us what that mechanism was? Yes. How did we determine that? By starting with the kinetics. So the 2 stands for bimolecular. So the rate equation has the nucleophile to the first power, the alkyl halide to the first power, and so this is a bimolecular reaction. And how do we know that it's a what do we do to conclude that it's a bimolecular reaction? We go back because this was our mechanism, right? What is the key step in the mechanism? Well, this is a 1-step reaction. So let's come back here. Here is my 1-step concerted mechanism. How many reactants are there in this? There are 2, the nucleophile and the alkyl halide. That makes this a bimolecular reaction. Okay, so kinetics comes first, and then your mechanism must be consistent with that kinetics. And typically we try and choose the simplest mechanism. It's called, the simplest explanation to a phenomenon is called Occam's razor, right? The simplest explanation is the one that's usually true. In mechanistic chemistry, we have the same thing. We try and come up with the simplest mechanism that explains our results. And so in this case, the nucleophile attacking the alkyl halide is the mechanism from the kinetics. Okay. Now, the reactivities for this reaction, for an SN2 reaction, are the following. If we measured the rate, what we would find is that a primary alkyl halide, now remember, what are primary alkyl halides? They're where the halogen is attached to a primary carbon. What's a primary carbon? It is a carbon with only one alkyl group or one carbon attached to it. Halogens don't count. So primaries react the fastest, tertiaries react the second fastest, and it turns out that secondaries react the second fastest. Tertiaries don't react at all in SN2 reactions, nor do what are called vanillic halides, where the halogen is attached to a double bond, nor when a halogen is attached to a benzene ring. That benzene ring has a circle in it. When we talked about a benzene or aromatic ring, we had 3 double bonds alternating. So those do not undergo SN2 reactions. And so this would be another mechanistic piece of evidence that we would get. We would say, okay, our mechanism has to be consistent with the fact that primaries react faster than secondaries and tertiaries do not react. So let's try and explain that with the mechanism. So in this case, in the reaction of alkyl halides, what we find is the reactivities of the halides is based solely on the number of alkyl groups that are attached to the carbon atom. So for instance, this is a primary carbon. It has one methyl group. If the nucleophile is going to come down the trajectory of the carbon-halogen bond and attack, one alkyl group isn't really going to block that carbon too much. So that, of course, is going to be the fastest reaction for the backside attack. Now, if I begin to put alkyl groups in these positions, I'm going to begin to block that carbon, so we would expect the reaction to get slower, and at some point maybe not even happen. So now let's go to a secondary. Put 2 methyl groups here. You can see now I'm cutting down on the ability of the nucleophile to get to that carbon. If I go to a tertiary, or if I make a really big sterically hindered molecule like this tersh-butyl group, now I've almost completely blocked it. And this would not undergo by SN2, nor would a tertiary halide with 3 methyl groups. I can't really get to that carbon, and so if the backside attack is the mechanism, then this tertiary halide would not undergo SN2, which it doesn't. So the idea that steric hindrance around this carbon, number of alkyl groups, and the size of the alkyl groups does cause an issue in terms of reactivity. So that is consistent with an SN2 backside attack concerted one-step mechanism. Okay, so that's how these rates of reactions also help us say, yes, it occurs by backside attack. Now, the way we know that backside attack occurs as opposed to front side attack, and let me just draw what would front side attack look like. Front side attack would be if I took this molecule with my halogen leaving group and I reacted it with something like hydroxide, I could say, well, why doesn't hydroxide come in and kick the bromine off from the front side? Or maybe it's a mixture of front side and backside attack. How do we know that it is indeed backside attack? And I'm talking about this after the fact. If I was studying this mechanism, I would sit down and go, I wonder if it's front side or back side, and then I would think about a way to test that. So the way we know that backside attack is the way that this reaction goes is I take, for instance, this R2-bromobutane, and I know what its specific rotation is, and I take and I react it with hydroxide, and then I determine what is the optical rotation of the final product. And now we can think about, well, what would happen in this case? Now, if we got a 50-50 mixture of front side and back side attack, what would happen? I would get a 50-50 mixture of the R and the S products, right? Because the backside attack in this case is going to lead to the OH group being here, and it's going to lead to what we're going to call inversion of configuration in a minute. If the OH attached from the front side, it's just going to replace the bromine, and the original R configuration would stay the R configuration in the product. So if you have a mixture of front side and back side attack, then what you would get is a 50-50 mixture of R and S. What do we know that as? A racemic mixture. And so we would get 0 degrees rotation for our specific rotation. So when we do this experiment, we don't get 0 degrees, so therefore it's got to be front side or back side, but it is not both equally. So then what we do is we look up the specific rotation of S2-butanol, or butan-2-ol, and we look up that specific rotation, and when we do this experiment, we find that the product matches with that specific rotation of the S enantiomer of 2-butanol. And so then we conclude that the R configuration became the S configuration in the SN2 reaction, and that's what we call inversion of configuration. And so this was done experimentally to show that this molecule underwent inversion of configuration, and indeed the nucleophile attacks from the backside, not the front side, and not 50-50. So that confirms the fact that we do have backside attack. Now, there's an orbital reason why we get backside attack, and I'll show you that to you now. So remember that for our carbon-bromine bond, the bromine would be sp3 hybridized, as would the carbon. And so if you looked at the carbon, in this case, with its sigma bond between the sp3 hybrid orbital of the carbon and the sp3 hybrid orbital of the bromine, remember that there's this little teeny tiny sp3 orbital that we usually ignore. We're not going to ignore it in this case, because here's what happens. The hydroxide comes in, and that hydroxide, of course, is sp3 hybridized. And so the way we form bonds is by overlapping orbitals. And so the reason that backside attack occurs in this case is because the hydroxide is going to come in with its sp3 hybrid orbital and overlap with the little teeny tiny orbital of the sp3 orbital of the carbon. And so in order to form that overlap and then kick the bromine off, you need to have this occur by the backside attack, because that's where the other part of the sp3 hybrid orbital is that we normally ignore, and we can't ignore it in this case. So that's why we actually get inversion of configuration and backside attack. Okay, so let's write a mechanism for this SN2 reaction. And so first I start with my arrow, and I say that my arrow has the OH minus. The minus charge is going to come in and add its pair of electrons to the bromine. And then this bond is going to break, and that pair of electrons is going to go in this case to the bromine. So the pair of electrons is coming in from the oxygen to form the OC bond. The carbon-bromine bond is breaking. So our transition state is always going to look like this. The carbon is always going to be trigonal bipyramidal, so it'll always have a bond in the plane, a bold, and a dashed. It does not matter if where you put the bold and the dashed. You could write it like this as well. We have a partial bond from the carbon to the nucleophile, and we have a partial bond from the carbon to the leaving group. And so either one of these would be fine. The dotted line then is what? That's the partial bond of forming the CO bond and breaking the CBr bond. And then what's attached to this carbon? What's attached to that carbon is a methyl group, an ethyl group, and a hydrogen. And notice in this case, since I started with a particular stereochemistry or chirality of this carbon, I need to make sure that the groups go in exactly the proper positions. So in this case, you could also write this with the CH3, CH2 on the bold, the hydrogen on the dashed, and the CH3 on the in the plane. So this is the transition state. So in essence, I'm forming a CO bond, I'm breaking a CBr bond, those are the partial bonds. And then I'm going to form as my final product the OH. And now this inversion happens. So instead of the CH3, the H and the ethyl group being pointed towards the nucleophile, they're now going to be pointed away from the nucleophile in the tetrahedron. And so this is the inversion of configuration. And there is a video in Canvas from, I believe, the University of Surrey in England, where they have a nice video showing the flattening out of these groups to form the trigonal bipyramidal geometry. And then basically, as the bromine leaves, these groups move and then end up forming this, end up in this direction. There was a time when you could think about this as an umbrella folding inside out. So for instance, up here, if I thought about my umbrella sort of looking like this with my invisible handle there, then as the hydroxide comes in and attacks, my umbrella is now sort of flat like that. And then down here, my umbrella has now blown inside out. So that's the inversion of configuration. So what we do is we average bonds and we average charges. And you can also average the bonds by just saying which bond is being made, which bond is being broken. Those get the dotted lines. But if I wanted to average bonds, I would say there is 0 carbon-oxygen bond. There is 1 carbon-oxygen bond. Therefore, what is the average? A partial bond. 1 carbon-bromine bond. Down here, the bromine would be a Br minus. 0 carbon-bromine bond. The average, partial carbon-bromine bond. Now, we also need to average charges for our transition state. So oxygen is -1, oxygen is 0, average, delta minus. Bromine is 0, bromine is -1. What's the average? Delta minus as well. So that is how we would get the transition state then from this SN2 reaction. All right. So that's our transition state, and it shows the inversion of configuration. If I don't give you the stereochemistry of the molecule, then you can basically put the groups anywhere you want. But if I show the stereochemistry using bold and dashed wedges, then you need to show the groups on their correct wedges as it inverts. And just in case you're curious, what's the stereochemistry of this molecule right here? Well, hydrogen is 4, bromine's 1, ethyl's 2, methyl's 3. So going from 1 to 2 to 3, this is our R configuration. And down here, hydrogen is 4, oxygen is 1, ethyl's 2, methyl's 3. In this case, 4 is now behind me. So going from 1 to 2 to 3 is now counterclockwise. So yes, the chiral center went from R to S in this inversion of configuration of this SN2 reaction. Okay, so that's how we would write the mechanism, and you will get practice doing that. All right, so let's summarize SN2 reactions. Number 1, they are bimolecular substitution reactions, and that means that the kinetic rate of forming the substitution is the alkyl halide to the first power and the nucleophile to the first power. The mechanism involves a backside attack of the nucleophile to form the trigonal bipyramidal transition state, and then kicking off the halogen, the leaving group, to form the substitution product. Because the backside displacement is dependent upon steric hindrance, the fastest are primary, second fastest secondary, and tertiary halides, and also the benzene rings and halogens attached to double bonds do not react in SN2. And the SN2 reaction of an optically active halide, meaning a single enantiomer, results in an optically active product, but it involves the inversion of configuration of the chiral carbon. So those are the 4 key points of an SN2 reaction. Okay. All right, so now to sort of, and we're going to be using these topics that I'm going to talk about here now in SN1 or SN2 and then the upcoming SN1 reaction. So let's talk a little bit about nucleophilicity and leaving groupability. And what I'd like to talk and what I'd like to outline here is what makes a so-called good leaving group and what makes a poor leaving group. And then what makes a strong nucleophile and what makes a weak nucleophile. So what factors go into this? And the easiest thing to start with is leaving groupability is based on one thing. Leaving groupability is based on one thing, it's basicity. And it is basicity inversely. So what does that mean? That means that a strong base is a poor leaving group. And a weak base is a good leaving group. So now what we have to do is now we have to define what I mean by a strong base and what I mean by a weak base. And just as kind of a review of general chemistry, what did strong base mean? Strong base meant something like, what's a typical strong base that we talk about? How about hydroxide? Hydroxide completely reacts with water to form water and hydroxide. So a strong base then is going to be something that reacts with water to pull off a hydrogen. Now, what is something like a chloride or a bromide? What are they? Now, in my world, I call these non-bases. And you may say, well, we didn't talk about non-bases in general chemistry. I know, that's because I don't rule general chemistry. If I did, we would have 3 categories of acids. So let me talk a little bit about acids, because if you remember from general chemistry, a strong acid has a certain type of base, a weak acid has a certain type of base, and let me define this out. So what's a strong acid? A strong acid is something that completely dissociates in water. It completely dissociates in water. So something like HCl. What happens when you react HCl with water? You get hydronium ion and you get a Cl minus. Is there any equilibrium here? There is, but we normally treat this as if it was 100%. It's not quite 100%. But let me come back to that in a moment. So I'm going to put the words completely in quotes here. So HCl completely dissociates in water. Now, what about something like HF? When you react HF with water, what happens? You get an equilibrium between H3O plus and F minus. So HF was considered a weak acid. And so what about weak acids? They partially dissociate in water. And what do we mean by partially dissociate? We have this equilibrium constant that's formed. Now, if you were really remembering about general chemistry, you would say, oh no, these are ice charts. And yes, we would fill out ice charts for the reaction of a weak acid with water, but we're not going to go that far in organic. Other than to say a weak acid partially dissociates, a strong acid completely dissociates. Now, strong acids like HCl, what is the conjugate base? What's the conjugate base of a strong acid like HCl? It's Cl minus. What happens when I put Cl minus in water? Does Cl minus deprotonate water to make hydroxide? No. No, I get basically no reaction. So is Cl minus acting as a base? No. So that's why I consider it to be a non-base. So in my world, the conjugate base of a strong acid like HCl is a non-base. It doesn't react with water to form hydroxide. And what is the conjugate base of a weak acid? Well, the conjugate base of a weak acid, if I took F minus and I reacted F minus with water, what would happen? I would get an equilibrium with HF and hydroxide, right? I would get that equilibrium reaction. So what is the conjugate base of a weak acid? It's a weak base. And this violates all English, right? What's the opposite of strong? Non. What's the opposite of weak? Weak. So it doesn't match up with English, but it matches up more with the reality of acids and bases. So I consider these chloride, bromide, iodide to be non-bases. What would be a weak base? Fluoride. What would be kind of a stronger base? Hydroxide. And so when we look at the periodic table, basicity goes in the following direction. As you go from right to left on the periodic table, basicity increases. Basicity increases as you go from right to left. And what that means is, that means that a C minus is the stronger base than an N minus, which is stronger than an O minus, which is stronger than an F minus. As a matter of fact, in organic chemistry, C minus and H minus are the strongest bases that we're going to get. N minus next, O minus, and F minus. So as we go from right to left, basicity increases, which means leaving groupability decreases. So that means a C minus is a C, having a group leave as a C minus or an H minus is not going to happen. So C and H groups, they are never leaving group. An O can leave only under certain conditions, but oxygen as a leaving group is going to be poor as well. So what are our best leaving groups? The halogens. Now, going up and down the periodic table, what happens? Well, if you go down the periodic table, what happens to acidity? Acid strength does what? It increases, right? HBr is a stronger acid than HCl, which is a stronger acid than HF. You might say, really? Or HI is even stronger than HBr. Well, in general chemistry, when we say that HI, HBr, HCl completely dissociates, you can measure the difference between HI dissociating, HBr, and HCl dissociating. They're almost complete, but not exactly. So HI does dissociate more than HBr and HCl. So the acidity increases with HI being the stronger acid. And what does that mean for basicity? That means for basicity that going up the periodic table, that means that the basicity then does what? If acidity increases going down, basicity will increase as we go up. And it will decrease as we go down the periodic table. So if acidity increases and basicity decreases as we go down the periodic table, what's the best leaving group? I minus. So in terms of the halogens, I minus is a better leaving group than bromide, which is better leaving group than chloride, which is better leaving group than fluoride. And these would all be considered good leaving groups. Oxygen poor, nitrogen poor, carbon, hydrogen ain't leaving. I'm going to take a step back here for a moment, just think a little philosophically about this. Remember in sort of our naming and at the beginning of this class how we said, well, an alkane is just a skeleton that we hang functional groups off of? Well, think of exactly how chaotic organic chemistry would be. And you may think it's chaotic now, but how chaotic would it really be if you could have a carbon or a hydrogen group get displaced or substituted in a molecule? It wouldn't act as a skeleton anymore. So whatever the design of organic chemistry is, having the carbon hydrogen as the skeleton means that the carbon and hydrogen better not leave. And so they don't, because they're such strong bases and that inverse relationship holds. Can we make a nitrogen group leave in the future? Can we make an oxygen group leave in the future? We can as well. But right now, halogens. So what would be the best leaving group for a halogen? I minus. Okay, so that was leaving group ability. But in order to understand leaving a group ability, we need to understand the periodic trend. We also need to understand then that leaving group ability is based on one thing: basicity inversely. Now, what about the idea of a strong nucleophile? Well, nucleophile strength is going to depend on what is your relationship on the periodic table. And you may say, what are you talking about? So now let's talk about the nucleophilicity, which is strength of nucleophile. So when you are comparing bases horizontally, on the periodic table. That means in carbon, nitrogen, oxygen, and fluorine. When you're looking at relationships horizontally, then the stronger base is the stronger nucleophile. So in a horizontal relationship, that means that a C minus or an H minus are not only the strongest bases, they are also the strongest nucleophiles, followed by an N minus, followed by an O minus, followed by an F minus, and then followed by the rest of the halogens. Okay, so horizontally, nucleophile strength is directly related to basicity. However, experimentally what's found is that for vertical relationships, that iodide is a stronger nucleophile than bromide, which is stronger nucleophile than chloride, which is then stronger than F minus. So this is in terms of nucleophile strength. So when you're on the periodic table, then it's opposite. It's not according to base strength, because remember, we said that F minus was the strongest base and I minus was the weakest base when we talked about leaving group ability. So what's going on here? Well, when we look at vertical relationships, we are looking at, when we're looking at a vertical relationship, we are using what is called polarizability. What's polarizability? I call it squishiness. And what's squishiness? It's the ability to squish something, to change its shape. So what happens is this. Let's go back to the idea of a nucleophile coming in, reacting with the little teeny tiny sp3 lobe of the carbon in an SN2 reaction. What I'd like to do to form the strongest bond in the transition state is to be able to squish the electron density down into the smallest possible area. So what I'd like is I'd like a higher electron density in this orbital. Well, that's going to require being squishy. And so for the iodide, its orbitals that are making up its sp3s are actually in this row on the periodic table that's much lower. So how tightly are the valence electrons in iodide held to the nucleus versus bromine versus chlorine? Well, as we go down the periodic table, what happens to the size of the ion? The size of the ion gets larger. Why? Because there's more electrons, there's more shielding, right? These valence electrons are farther away from the nucleus. The farther they are from the nucleus, the less tightly they're bound, and the more squishy the electron clouds become. Whereas a fluoride is, those valence electrons are held much more closely to the nucleus, and they don't deform. They don't have the ability to deform as easily. So the bigger the ion, the more squishy, the more polarizable it is. And the more I can compact the electron density in this orbital, the stronger the bond will be in an SN2 reaction in the transition state. So iodide's like a Nerf ball. You can squish it a lot. Fluoride's like a golf ball. It doesn't squish very much at all. So in terms of nucleophilicity then, when you're looking at the vertical position, that means as you go down, nucleophilicity increases, and as you go this way on the periodic table, nucleophilicity increases. So it really depends on whether you're talking about a horizontal relationship or whether you're talking about a vertical relationship. Vertical polarizability wins, and horizontally basicity wins. Which leaves us with a paradox for the halogens. Who is the best nucleophile? Iodide. Who is the best leaving group? Iodide. So what happens when you react a nucleophile with an alkyl iodide? Well, the iodide is a good nucleophile, but it's a good leaving group. What normally happens is you get some type of equilibrium. And so we probably avoid iodide as much as possible because of the potential equilibrium that we have. So that's the basics of nucleophilicity, leaving group ability. And the last thing that we'll talk about is solvent effects. So in terms of solvent effects on an SN1 reaction, we first of all have to talk about solvents. Well, remember, in an SN1 reaction, the nucleophile is reacting with the carbon attached to the leaving group to form the new nucleophile carbon bond and kick off the leaving group. That's the SN2 reaction. Because I have ions here, I need to use a polar solvent. Nonpolar solvents are not, this is not going to be possible in a nonpolar solvent because ionic substances are not real soluble in nonpolar solvents like hydrocarbons, like hexane or pentane. So first of all, I need polar solvents for SN2 reactions. But there's two classifications of polar solvents. There are protic polar solvents, and there are aprotic polar solvents. And I've never been a big fan of these terms. In graduate school, when we studied these kinds of things on the project that I did, I used what's called the Fred Bordwell method nomenclature, which protic meant hydroxylic and aprotic meant non-hydroxylic. And most books have not adopted that terminology, but I think it's more descriptive. So protic and aprotic mean basically hydroxylic and non-hydroxylic. But there's protons in all of these samples. So what do I mean by that? Well, what is an example of a hydroxylic protic solvent? HOH, water. Alkyl group OH, alcohol. Those are our protic polar solvents. Hydroxylic solvents is more descriptive because what do they have? Hydroxyl groups. What are the aprotic polar solvents? Well, they don't have hydroxyl groups. So some of those would be things like acetone. Or another one that's used quite a bit is replacing the carbon with a sulfur. This is called dimethyl sulfoxide, which is abbreviated DMSO. Other polar aprotic solvents are things like CH3 with a C triple bond N, which is called acetonitrile, or acetonitrile, either one. Some other Some other aprotic solvents would be, well, another one that's commonly used is this molecule, which is called dimethylformamide, which is abbreviated DMF. So these are examples of aprotic polar solvents or non-hydroxylic solvents. And so we break the polar solvents up into two classes. Now, which solvent is going to speed up or slow down an SN2 reaction? Well, let's think of it this way. I have two sets of ions here, a nucleophile and a leaving group. In this reaction, what I like to do is to not slow down the nucleophile attacking this carbon. So how do I not slow down the nucleophile? Well, I have a solvent that kind of just like solvates the nucleophile, but it solvates it very weakly. Why? Because the nucleophile is going to be surrounded by solvent molecules. It's going to have to get rid of them as it attacks this carbon and kicks off the leaving group. Well, which of these solvents is going to more weakly solvate the nucleophile? Everything that doesn't have an OH group. Because when you have an OH group, you've got a strong delta minus and a strong delta positive charge. So when you use protic solvents, what happens is that you solvate the nucleophile really strongly. This is going to be strongly solvating. And that's going to end up slowing down the reaction. So the nucleophile, if it's strongly solvated to a protic polar solvent, is going to have to get rid of that solvent before it attacks the carbon. And getting rid of it, if it's more strongly, solvating it, it's going to take more energy, and it's going to slow down the reaction. So in this case, what we do is we don't necessarily look at what is a positive effect, we look at a negative effect. And so polar protic solvents, by strongly solvating the nucleophile, they slow down an SN1 mechanism. SN2 mechanism. They slow down an SN2 mechanism. What about the aprotic solvents? They don't. So which solvent is an SN2 reaction going to go faster in? It's going to go faster in an aprotic polar solvent, because the aprotic polar solvent doesn't slow it down, whereas the protic polar solvent does. Okay, so that's how the solvent effects play a role in SN2. In the next lecture video, we'll start talking about SN1 reactions, which are going to have a different mechanism, and this is going to be reversed. We'll talk about why that is in the upcoming lectures. Okay, so that's the end of this lecture on SN2. We will pick it up with SN1 in the next lecture video.